Hello, this is Jim McKeith, and welcome to this session with Boian Mitov on Arduino, controlling Arduino devices. This session is going to be a bit longer deep dive. There's going to be about an hour and 20 minutes of presentation, and then we'll go into the Q&A. So be sure and put your questions in as you go. If you can't stay for the whole session, we will have the replay posted on the DelphiCon site, but hopefully you can stick around for the Q&A discussion at the end. So with that, I'll go ahead and kick the video off.
Hello and welcome to DelphiCon 2021. My name is Boian Mitov, the president of Mitov Software, and in this session I will show you how you can control Visuino programmed Arduino Manipulator robot from a Delphi application over Wi-Fi or Bluetooth. Here is the robot manipulator arm I will use in the projects. As you can see, it has 4 degrees of freedom controlled by 4 servos. It comes with Arduino Uno and potentiometer shield that also has connectors for the servos. It has 2 additional connectors for 2 more servos. It also comes with Bluetooth connector. We can install Bluetooth to serial module here. And it came with power adapter that I will use to power the robot during the experiments. The shield, for some additional information, allows also seating an Arduino Nano size board, but we will not use this feature. Important to know is that there is a jumper which allows the Arduino Uno to be independently powered from the potentiometer servo shield. We can expand the robot by installing the Bluetooth module on the connector, or we can install another shield underneath the potentiometer shield. In case there are conflicts with the pins, we can also replace the potentiometer shield with, as example, universal sensor shield like this one. If we wish, there are a variety of other shields that we can use to upgrade the module, as well as connecting other sensors and modules to the top of the shield, or if we use sensor shield, add even more sensors to the different connectors. The robot can be programmed both with the Arduino IDE and Visuino. Visuino is by far the easier way to program it. We can communicate with the robot from Delphi application multiple ways. The simplest way is using serial port over USB. Alternatively, we can use Bluetooth if we add Bluetooth module to the shield. If we install a Wi-Fi shield, we can also use Wi-Fi to communicate to the robot. Finally, we can replace the Arduino controller board with a different controller that has built-in Wi-Fi or Bluetooth. When working on a robot project, we are likely to encounter a variety of challenges. There are often shields using the same pins, causing conflicts when trying to use the shields. Some shields are simply not compatible with each other, and we have to look for alternatives. There are sometimes also electrical problems, such as power noise causing the boards to reset, bad wires, back connections, reverse plug connectors, and many others. There are also mechanical problems. Sometimes servos can get stuck, rods can get jammed, wires can entangle into the moving parts, or bolts and nuts getting on the way of the movement. When doing communication, there are also a number of things that we have to pay attention to. We have to be careful to select the right serial communication speeds, Wi-Fi host names, port numbers. In Bluetooth LE, we have services and characteristic get values that we have to enter correctly. When developing the Delphi projects, we also have to pay attention to project settings. When we work as example with Bluetooth, we have to make sure we have the right Bluetooth permissions properly set. Finally, as usual, there are always a variety of coding challenges and surprises when working with the hardware. In this session, we will use animation timeline to control the robot. The timeline has channels controlling the servos, and we will need to have the right values to position the servos properly. The simplest way to achieve that is to manually position the robot, controlling the servos with the potentiometers, and once positioned, to record the values so we can use them in our animation timeline. For this, we'll write a simple Visuino application for the robot and a small Delphi application to display and record the values. We will start with new Visuino project. Click on this drop-down button and select Add Shields. This will allow us to add shields to the Arduino. Expand the robot's category and select the Sinuink for potentiometers and servos shield. Click on the Add New Item button to add the shield and close the editor. This will add the potentiometers and the servos from the shield to the Arduino. Now I will add a packet component to send the potentiometer values to the serial port. The packet is capable of packaging multiple channels together to send over single serial communication. And now click on this button, select Analog Channel and add 4 of them to the component. Close the Elements Editor. Now I can connect each of the potentiometers to the corresponding channels. And the output of the packet to the input of the serial communication. To make sure the packet communication is reliable, it is highly recommended to always add header marker. This will allow the beginning of the packets to be discovered and the communication to automatically synchronized. Not adding head marker may lead to unreliable communication. We can simply connect the potentiometers to the servos, and I often do that. However, if we move the potentiometer too fast, the servo may become a little jerky. It is better to smooth the operation by adding ramping components. I will add 4 ramp to analog value components. Select the components in the toolbar, right-click and select Out Multiple Components, and you can enter the number of components you want to be added. And I will connect them to the servos. I will set the initial value to 0.5 to have the servos centered. And now all I need to do is connect each potentiometer to the corresponding ramp to value component. The project is ready. Before we upload the code to the Arduino, we need to make sure that the Arduino and the servos are powered separately. The servos consume quite some power and it is very dangerous to power them from the Arduino. Even if we don't damage the Arduino, when the servos start moving, we'll have enough power noises that the Arduino is likely to reset. For this, we'll use the power adapter included in the kit to power the servos, and we'll use the USB to power the Arduino, disconnecting this little jumper here. Now I'll go ahead, connect the USB port, switch to the Build tab, select the correct COM port where the Arduino is connected and click on this button to upload the code. If necessary, the code will first be compiled before uploading. Now, as you can see, I can use the potentiometers to control the robot and position it the way I want. I can also connect to the COM port and monitor the positions as example on the scope. The Visuino project is ready. Now we'll create Delphi application to receive, display and save the values. I have already started a new VCL project. To receive the data, we'll need to add a COM port component. The component is part of the communication lab. Then we'll need to unpacket the 4 channels for the 4 servos. We'll use unpacket component, also part of communication lab. We can double click on the unpacket and add 4 floating point channels. Make sure we set the same header marker we used in the Visuino. To work with the 4 values received by the unpacket, the simplest way is to add 4 SL generic real value components. The unpacked channels have events, however, the generic real value components are much easier to work with. Now connect the COM port to the unpacket and the 4 floating point channels to the generic components. Since I plan to display the values from the components, I will need to synchronize them with the main thread. I will set synchronization as single buffer since we just want to display the most current value. By default, the COM port component as well as the serial communication in the Visuino will have a speed of 9600. This speed should be sufficient for this project. Double-click on the COM port component to select the COM port where the Arduino is connected. Now I will add 4 TEdit components to display the values. For each of the generic filters, I'll double-click to create the onProcessData event, and I will assign the text of the corresponding edit based on the value received by the filter, and I will do some formatting to display it with limited precision since the values will be somewhat noisy. The code in the 4 events is identical except the edit that is being accessed. Now we can try to run our project and see if we will receive the values from the robot. As you can see, we are reading the values, and if we move the robot, the values will change correspondingly. We can record the values from here. However, I will make the project a little bit easier to use. I will quickly arrange the key edits, set them to be anchored to the right, add a memo component, anchor it to the 4 corners so it will resize with the form, set the vertical scroll bar to be visible, and now I will add 4 buttons. Again anchored to the right. For simplicity, I will use copy and paste to replicate the button with the settings. We'll set the caption of the first button to be add, second clear, third load file, and the last one save file. Before I do anything else, I will add one more edit to add nodes for the position, again anchor it to the right. I will name this edit node edit. And now I can start adding the code for each of the buttons. For that button, first I will add all of the text from the edits on a single line, and then I will clear the node edit text so I can enter new information. The clear button will simply clear the lines, and for the load and save I will need load and save dialog. So I open dialog and save dialog. For each of them I will set default extension and populate the filter. And for the load button, if open dialog execute succeeds, we will load the lines from file. We'll do something very similar for the save button, except it will be the save dialog, and instead of loading we will be saving. Before we try the project, we will just clear all the values from the edits and the memo, and now we can try the project. We can position the robot at the position we would like to start, enter a name for the position, as example start, and click the add button. As you can see, the position is recorded in the memo. Now we can move the robot to the next position. As example, just closing the claw. Type a note and click add. This way we can start building our timeline for the animation. And we can save at any point our recording and continue later. We can open the recording in Notepad when we populate the timeline. This should make our life much easier. Now we can go ahead and record all of the movements in preparation to use them for the animation timeline. Once we have all the robot positions recorded, we can start creating a timeline. For this, we will use the timeline component from Animation Lab. Again, I have already started and saved an empty Delphi VCL form project, and now go ahead and add a timeline component. I'll double click on the component to open the timeline editor. And I'll add 4 real timelines to it. I have prepared a notepad file with the values we will use for the timeline. I will populate the values in cubic spline. We can do it with linear interpolations, however, cubic spline will make it much smoother and more interesting. So I'll go ahead and add a cubic spline. And I'll add 4 points inside the spline. I'll repeat this for each of the channels. Next, I will position the points to spread relatively evenly. We don't need to be very precise about this. We can always move them a little bit around if not happy. Our points look quite good. Now I can expand a little bit the timeline, setting the interval to 5 seconds. To make our life easier, I will make RadStudio to dock on one side and dock the notepad on the other. Now I can go ahead and start populating the values. We need to set the initial values into the initial values for each of the channels. For the final values of each of the splines, we'll put the final value of our sequence. For the first point, we'll put the value from here. We will repeat this for the rest of the points. our timeline is finally done. Since in my case I recorded it from left position all the way to right position, I would like to also add two linear movements to move the robot from right to neutral central position and from neutral central position to the left. For this, I will simply add a couple of linear interpolations at the end for each of the channels, and I will insert linear interpolation at the beginning. And I will do a few adjustments for all of the points. To get those positions, I again use the same recording application we did earlier. After some experimenting, I am finally quite happy with my timeline. To be able to start our sequence, we will need to add a button. We can write code to start the timeline with the button. However, instead I will use Visual Live Binding with OpenWire. I will select Add New Visual Live Binding for the timeline, search for Start, and add multi-sync pin for it. Select the button, switch to the events, and add clock source pin for the on-click event. Switch to the OpenWire view and connect the button to the timeline. To make sure the timeline doesn't start as soon as the application starts, I will set the enabled to false. The project is ready to start adding communication with the robot. The simplest way to control the robot from Delphi is to use the serial port. For this, we'll need to create a simple Visuino project to receive the data and control the servos. Start with New Visuino project, add the shield, add 4 ramp to analog value components to smooth the servo operation, connect them to the 4 servos, set initial value to 0.5 to make sure the servos are centered initially, and now we will need to add unpacked component to unpack the data that we will receive from Delphi. We need to add 4 analog channels for the 4 zeros. Set header marker. Make sure we remember the values we set here so we can set them the same in Delphi. And connect the 4 channels to the RAM to value components. Connect the input of the unpacked component to the output of the serial port. Since we'll be sending quite some data, we should increase the speed of the serial port. As example, to 115,200. This should give us relatively fast and reliable communication. Switch to the Build tab and make sure that the correct COM port is selected. Click on the Upload button. If necessary, the code will compile and then upload. The code is uploaded and our robot is position centered. Now, in our Delphi application, we can add the components to communicate with the robot and send the timeline data. We will add a packet component to packet the 4 channels together. Make sure we add the same header marker that we set in our Visuino project. Double-click on the component to add 4 floating point channels. Not to overload the communication, we will set some relatively low but still reasonably high clock rate for the data. For clocking, we will use a clock component. And we'll connect the clocking component to the packet component. We'll set it to send 15 samples per second. This should be fast enough without overloading the communication. If we don't connect the clock, anytime data is changed, it will immediately be sent over the serial communication. Sometimes it could easily overload the communication. I will also connect the 4 channels from the timeline to the packet component. Now all I need is to add a COM port component to send the data. Make sure I select the right COM port and the same speed we set in our Visuino project. Connect the output of the packet component to the input of the COM port and our project is ready. If we want, we can add a couple of gauges to show us the current positions of the zeros. I will set the max value for the gauges to 1 and I will connect the gauges to the corresponding channels. and we can test the project. Click on the start and see the movements of the robot while monitoring the movements on the gauges. Next, we'll try to control our robot over Wi-Fi. For this, we will need to install a Wi-Fi shield. I will use the Adafruit Airlift Wi-Fi shield. This is a very nice shield that has a dedicated ESP32 based Wi-Fi controller on board. However, unfortunately, this shield is not compatible with the potentiometers and servos shield. Some of the pins are used on both shields, and if you try to use them together, you will have conflicts and the Wi-Fi will not work. For this, I will also replace the potentiometer servo shield with a generic sensors shield like the one shown on the picture. When we install the new sensor shield, we will need to connect the servos to pins that are not used by the Wi-Fi shield. For this, we will need to figure out which pins are available for us to connect. For this, we can use Visuino to help us. We'll start new project and we'll add the Airlift Wi-Fi shield. The shield will immediately show which pins are in use. If we connect anything on the shield, it will also immediately gray the pins. So at the moment we can use any pin that is not gray. I will also avoid using the chip select pin for the micro SD. So this means that the best pins for us to use will be 9, 8, 6 and 3, going sequentially. We'll install the servos on these pins. Before we start replacing the shield, make sure to disconnect all the power and USB from the Arduino and the shield. Next, I will go ahead and carefully disconnect the servos. I will try to keep their order in terms of cables, so it will not be confusing when we connect them to the sensor shield. Now very carefully grab the shield itself. Avoid grabbing the potentiometers because they are fragile and you can easily tear them off the shield. The best points are probably here, here and here. And start carefully unplugging it from the Arduino. Put the shield aside and bring the Airlift Wi-Fi shield. Make sure you have a shield that has both male and female connectors. I have even made a video how to install the proper connectors on the shield. I will post it in the resources at the end of the slideshow, and also will post under the video when I post on YouTube. Next, carefully align the shield with this protruding outside matching on both boards and this connector matching the Arduino connector underneath. And carefully plug the shield, pressing on the connectors. The shield is properly installed. Before I install the sensor shield, I will need to connect power to it, since we would like to be able, the same way as with the potentiometer shield, to have the servos being powered separately from a power supply, using this jumper to separate or join the two powers. I will use this connector with wires and a small screwdriver to untighten the connector. The shield, this particular one, has the VCC and ground clearly marked. I have checked and the colors on my particular cable match. Make sure by measuring the voltage on the cable when connected to the adapter that this is positive and this is negative, and connect properly to the connector, the red to VCC, and tighten, and the black to ground. And tighten. The shield is ready to be installed on top of the Wi-Fi shield. Again, this uniquely looking side of the shield with this sticking part has to match the same sticking parts on the Arduino and the Wi-Fi shield. Place the shield so it is properly aligned with the connectors. Like this, and plug it in place until it snaps. Now we'll go ahead and install the servos. Hopefully I still keep the order correct. Now before you rush to plug them in, pay very careful attention to these letters here. This is ground, V is power, VCC, and S is signal. Make sure you properly orient the connectors and don't plug the servos in opposite order. It is a bit confusing because in the potentiometer shield the order is reversed. Signal is here, where signal on this shield is here. So you have to reverse the connectors when you unplug from this shield and plug on this shield. Pay attention to the order. This is one of the pitfalls of working with robots. So let's consult with our nodes. The first connector will be connected to signal number 9. Connector number 9 here. So this servo is connected to number 9. The next servo is connected to number 8. Then number 6. And again, remember what I said about the pitfalls of reverse connectors? I succeeded for a brief moment to connect them with the wrong orientation. The orange has to be on the side of the signal. The next one goes on number 6. And the final one will go to number 3. If I have not messed up the order of the servos, everything should be fine. We'll discover very soon when we start testing the robot. Our shields are installed, the servos are connected, and we can start testing the robot. Can try to make sure that the cables are not impeding the robot. As I mentioned earlier, entangled cables are a common danger when dealing with robots. I need to make sure there is enough slack to this servo not to impede the movement. The robot should be ready for Wi-Fi control. Make sure the connector here is disconnected, the jumper is disconnected, so the power from the shield will go only to the servos, and the Arduino and all the electronics will be powered through the USB port. This way, preventing any damages to the USB from the two power sources fighting each other. Now we can go ahead and create our Visuino project for the Wi-Fi control. I will start with new Visuino project. I will click on this button to add Adafruit Airlift Wi-Fi shield. Configure the shield. For this, we'll need to add access point to have the Arduino connect to it. And enter the password. Next, I will add a socket. We have variety of options. I have decided to make my Delphi application to be server and have the robot connect to it. This way I can have few robots connecting to the same server and being controlled at the same time from the same application. So I will add TCP/IP client socket. For host, I will enter the name of my computer on the network, and I will enter a port 222 as example. Our shield should be fully configured. Next, we will need to add servo components. Search for servo in the toolbar, select the servo component, and add 4 such components. We will start adding them from the bottom to the top. So servo 1 will be connected to digital pin number 9, servo 2 to digital pin number 8, 3 to 6, and 4 to 3. This matches the order of the servos on the potentiometer's servo shield. Now, to make the servo movements smoother, I will add ramping components. Select ramp to analog value from the toolbar and add 4 of them. Connect them to the corresponding servos. Next, we will need to unpacket the data. Add unpacket component, click on the Tools button to open the editor and add 4 analog channels. Close the editor. Make sure you enter some values for the head marker and make sure you remember the values so you can enter the same values later in Delphi in the corresponding packet component. Connect the channels to the ramp components. To make sure the servos will be positioned centered when you power the robot, set initial value for the ramp to value components to 0.5. Now I can connect the input of the unpacked component to the output of my socket. Our project is ready and we can upload it to the robot, but we can do one more improvement. The shield has RGB LED on it. We can use the LED to indicate our connection status. For this, I will add digital to color converter. Set the false value to red and the true value to lime. Connect the output of the component to the input of the LED and the input to the connected output of the socket. The project is ready and we can upload it to the Arduino. Switch to the Build tab and make sure that the correct COM port is connected. Click on this button to upload the code. The code is uploaded and you can see that the Wi-Fi shield is trying to connect to the socket. Now we can go ahead and modify our existing Delphi project to send the animation timeline over Wi-Fi. Select the COM port and remove it. Instead of COM port, we will add a server socket. We will set the port of the socket to 222. Switch to the open wire diagram and connect the output of the packet to the input of the server socket. Now we can run the application. A Windows security alert is likely to pop up. We need to allow access for the socket port. If we connect power to the robot, you will see that the Wi-Fi shield will show red LED light. And within few seconds, when connected, the LED will turn green. Now we can try to control the robot. As you can see, it works. We can repeat again the same. Depending on the quality of the Wi-Fi, the robot sometimes will move smoother, sometimes jerkier. To control the robot over Bluetooth LE, in Visuino we can load the already created serial control project and simply change the serial port speed to match the speed of the HC08 module, typically 9600. The sensor shield that we installed on the robot for the Wi-Fi has connector for the Bluetooth module. Unfortunately, they have installed on my one male connector, which makes it a little bit more difficult to connect to the Bluetooth. I will need jumper wires. Instead, I'll go ahead and put back the potentiometer shield, which has the proper connector for my Bluetooth. I will go ahead, remove the shields. I can leave them connected together. Disconnect the servos. And connect the servos to the potentiometer shield. Make sure you orient the connectors properly. Pay attention that they are 180 degrees compared to the other shield. And go ahead and connect in the same order. Make sure that the signal is the white or orange wire and the minus is the black wire. All the connectors are in place, and yes, ground is properly connected on all of the connectors. Now I can go ahead and install the shield. Installing single shield is much easier than installing a stack of shields. Now I will reopen the serial port project in Visuino and change the serial port speed to 9600, which is the speed of my Bluetooth module. Make sure that on the sensor potentiometer shield the power jumper is disconnected, the Bluetooth module is not installed, and connect the USB cable to upload the code. Click on the upload button to upload the code. Now I can disconnect the USB, connect the jumper so we can power both boards from the same power connector. Take the Bluetooth module and make sure I install it matching the pins as described here on the board. VCC to VCC, ground to ground, TX to RX, and RX to TX. They have to be crossed because transmission on one board is receiver on the other one. Connect the power adapter and our robot should be ready to be controlled over Bluetooth. To control the robot over Bluetooth LE from Delphi, I will create a FireMonkey application. I will start by creating new multi-device application in Delphi. Select blank application, add 4 track bars, make them vertical. I'll start with 1 track bar, position it the way I want it, set the max to 1, the value to 0.5. Since the servos have values between 0 and 1, they're normalized. We will send values between 0 and 1 from the track bar. Anchor the track bar to left, top and bottom. And now I will use copy and paste to add 3 more track bars. And now arrange them roughly equally spaced. Next, I will add a shape indicator to show me when I am connected to the robot. I will use circle for this. To access the Bluetooth LE, I will need Bluetooth LE component. In order for the component to work, I have to enable the Bluetooth permissions for the project. Both Bluetooth and Bluetooth admin will need to be enabled for the Android platform. Since I'll be running Android, I need to also grant permissions at runtime. For this, for the form on create, I will need to add the following code. In order the permissions code to work, we'll need to add few units. We also need to provide these two methods in the form and their implementation. Now I will set the target to Android, in my case 32-bit. And I will make sure that I have selected the connected device. When we receive permission, we will start discovering Bluetooth devices. Now I'll go ahead and start adding code for the discovered devices. I have already prepared the code and I will quickly go over it. Here we will go through all of the devices and we will search for specific service. I will add the constants for the service and characteristic that we will use. I have them prepared. These are the service and the characteristic used by the HC08 to send serial data over Bluetooth. I will also need 3 variables to store my service, device and characteristic. So the code will go through all of the devices, discover the services, search for the service by get, and if the service is discovered, assign the device to the device variable, connect to the device, and search for the characteristic. If we discover the characteristic as well, we search it also by get. Here the two gets. If all is successful, make the circle lime color. And we can break the loop since we have discovered our device. The Bluetooth LE component requires also the Discover services to be implemented in order for us to be able to get the service. Loop through the services and simply access the characteristics in each service. To send the data, we will use packet component. Set head marker the same as in the Visuino project. Double click on the component and add 4 floating point channels for the 4 trackbars. To send the data, we will use generic filter. We will connect the packet component to the generic filter. Double click on the filter to get the on-process data. Here, if we have characteristics discovered, we will loop through all the items in the received buffer and will send them byte by byte into the characteristic. To send the values from the trackbars, I will implement a simple function. It will simply get the values of each trackbar, invert it, and then assign the calculated value to the corresponding element of the packet component. We will call this function onFormCreate and also in the onChange event for all of the trackbars. Any of the trackbars will call the same function. To specify how often the data is being sent, I will also add a clock component. I will set a rate of 10 times per second and I will connect the clock component to clock the packet component. By default, the Bluetooth is not enabled and we will need to enable it. Now I can go and run the app. Allow the Bluetooth. And now we are connected to the robot. And we can start controlling the servos with the sliders. We have Bluetooth control for the robot. So to recap, during the session I have shown you how to install and work with Arduino shields and modules, how to program the robot with Visuino, how to receive and record data from the robot with Delphi, how to create and populate animation timeline, and how to use it to control the robot. How to control the robot from Windows and Android Delphi applications, and how to communicate with the robot over serial, Wi-Fi, and Bluetooth communication. Here I have prepared a list of resources and more information for Visuino, the Mitov software components used in the projects, where you can find the robot and assembly video tutorials for it, links for the HC08 Bluetooth LE module, the Wi-Fi shield, the sensor shield, and information how you can solder proper pin headers to the Wi-Fi shield so you can install it between the Arduino and another shield. Thank you for listening. Once again, my name is Boian Mitov, the president of Mitov Software. My email is mitov@mitov.com, and here is the list of the Mitov software products: Video Lab, Video Processing Library; Audio Lab, Audio Processing Library; Signal Lab, Digital Signal Processing Library; Vision Lab, Computer Vision Library; Plot Lab, Data Visualization Library; Instrument Lab, Visual Instrumentation Library; Intelligence Lab, Artificial Intelligence Library; Logic Lab, Boolean Logic Library; Animation Lab, Universal Animation Library; Communication Lab, Serial and TCP Communication Library; Control Lab, Industrial Control Library; Visual Live Binding, Universal Visual Live Binding Library based on OpenWire; Mitov Runtime, a free Delphi library; OpenWire Studio, a graphical development environment for Windows; Visuino, a graphical development environment for Arduino controllers; Visuino Pro, a graphical development environment for Arduino-based industrial PLC controllers. Mitov Software also maintains a number of open source libraries, including OpenWire and iGDI+. And now it's time for questions and answers.
Okay, great. Thank you so much, Boyan, for your presentation. A few other people commented that they learned a lot. I did as well. As always, learn a lot from your sessions.
Well, thank you. Thank you everybody for joining.
So Omar asked if the robotic arm had to be manually assembled. It didn't come pre-assembled.
The version that I have came basically as a kit that I had to assemble, and I have actually posted video tutorials on how to assemble it. I included a link to the playlist with the video tutorials. It's multiple videos, obviously, for the entire assembly process. It's in the materials in the slideshow.
Okay, great. If anybody has any other questions, feel free to put them at the question panel here, and we'll do our best to get them answered. How much overhead does Visuino add to a project? So if you're making a project with Visuino, what is like the minimum overhead it adds versus just writing code from scratch?
I believe is generally speaking typically probably between -50 to -70%. It reduces your your overhead by generally speaking. Depends on how experienced you are. If you are very experienced, it probably is going to reduce your overhead by 10%. It generates, on average, it generates code that is better, even by compared to a code that I can manually write with all of my experience.
Wow. That's right. I remember you talking about how you reduced the code generation quite a bit.
Yeah, it uses a large number, and I'm constantly adding more and more code optimizations. The code looks quite complex, but once compiled, it compiles into very small amount of code, and the focus is exclusively on reducing the RAM usage. So since the read-only memory actually typically is not issue on the microcontrollers, the RAM, however, the read-write memory is the read-write memory is 1 second. The read-write memory, however, is usually significantly smaller and is very often the issue. So for flags and things like that, Visuino will use single bit. It will not reserve a whole byte, which is normal, right? If you declare a Boolean variable, it will typically use a whole byte. Instead, Visuino uses bit fields, and as a result, as example for flags, it will use single bit, and a single byte will be used between multiple flags. Same thing applies for other integers. If an integer goes between 0 and 15, as example, it will use only 4 bits. It will not use a whole byte for that, and so on and so forth. Those are just few examples of the optimizations that are used. So it reduces the code considerably using techniques that are very difficult to achieve with traditional coding practices.
Um, is there a way to import the saved data to the timeline instead of entering it manually?
Not at present. Yeah, not at present. It's a very good idea, and I have since I did this project. Usually, that's not how you use timeline, but since I did this project, I started thinking about the same thing. So I probably will add in the next version of Animation Lab some kind of import tool, also export tool, so you can export and import timelines easier. At present,
Sometime
it's
later today, then.
oh, well, yeah, probably a bit later today. Yeah, you're right.
The question here, I assume we need to put the first and last points in to make the spline work.
That is correct. The spline has ending point. It's similar to the other interpolations. So the starting point is always the point of the previous spline because they're in sequence, right? So you can have multiple, not spline, but the previous interpolation. You can have a mixture of interpolations, as was the case in this example. And you can also have stepping. You can step up and then step down and so on and so forth. So the previous value is the starting point. The ending value of the previous interpolation is the starting point, and the ending value of the interpolation is also the ending point for the particular spline. So that's why I first entered the starting point, ending point, and then populated the intermediate points for the particular spline.
Okay. Question here, how deterministic is the code generated by Visuino for the microcontroller? Is it yeah.
Deterministic in terms of what?
I'm guessing asking if you regenerate it multiple times in a row, how much is it going to change, or is it?
Oh, the code will, with a particular version of Arduino, the code will always be generated the same way. So the only thing that could be reordered, and that's due to some parts of the OpenWire architecture, sometimes the order of, as example, if you have two recipients of data, the order of the recipient may change between uh, what between different reopenings, but other than that, the code is practically always generated the same.
And I don't think you got into it. If you did, I missed it, about the difference between Visuino and Visuino Pro. And Visuino Pro gives you the ability to actually see the code and make your own custom code and stuff like that as well, right?
Yeah, I will cover the differences. Visuino Pro
aside from everything that Visuino has, of course, as you mentioned, the live code view. So you can constantly see how the code changes as you add new components and stuff. It has custom code components, which allows you to inject your own code in the project. It supports sub-diagrams, so you can have one main diagram and you can have multiple sub-diagrams, and you can have sub-diagrams of the sub-diagrams, so it's a full hierarchy architecture. And of course, you can have multiple instances because each sub-diagram is represented as component. You can have multiple instances of sub-diagram. So it allows you code reuse effectively and refactoring. It also includes a Modbus support for industrial automation, and it comes with Fourier transformation components and few other GUIs. Those are the main differences between the standard and the pro version. It's oriented more toward industrial usage than casual usage, but of course, I mean, if you want to make more advanced projects, that's where it comes.
Now, someone commented here that this seemed like a good tool to teach, introduce youngsters to real-time programming. But it's also, which I agree with, but I think it's similar to like Scratch and some of the other visual tools out there. But the thing I love about Visuino is that it's also good for like more complex, like you said, industrial, even professional level applications as well. So it kind of covers the full spectrum.
Correct. And again, because of the level of optimization that it does over the code, it allows creating code in terms of complexity and projects in terms of complexities that are unheard of in the microcontroller world otherwise, even by experienced developers. After spending months of work, they will have difficulty achieving what could be achieved literally in few minutes using Visuino in terms of complexity of the project that can be achieved.
So the question about deterministic, he says, how deterministic is the code on the microcontroller in milliseconds?
Oh, well, the code, well, again, I mean, this is a microcontroller, so it's not a, it's since there is no operating system, the code will practically execute repeatedly with roughly the same delays. In microcontrollers, there are a variety of challenges that will affect timing. And typical examples are even communication with devices, even I2C devices. The communication may vary in terms of how long for the packet it takes to go back and forth. Even worse with serial communication, obviously. So those things are going to affect the timing. The code otherwise is not worse. It's definitely better than what can be achieved in general, in theory, in a microcontroller, given the limitations of the microcontroller. And on another hand, Visuino does support to a great extent interrupts. So for things that are time sensitive and require interrupts, Visuino will automatically generate the interrupt handling code and will make them a little bit more deterministic. As example, rotary encoders and things like that, they work quite well with Visuino because Visuino will do its best to generate interrupt code for them. So that's the best I can say. Again, it depends a lot from controller to controller. Some controllers, let's put it at that, some controllers are more deterministic than others. And there are a lot of studies that I have watched online which compare how deterministic, assuming this is the term we want to use here, or how real-time one controller is versus another.
I know you're a big fan of the ESP32s. I am as well. A couple of people commented they use those. Is there a microcontroller you found that is probably the most reliable real-time deterministic controller?
Well, ESP actually is not the best in terms of, sorry, as I mentioned, let's do a bit of Marco Rubio here. as I mentioned in the videos that I have watched, they criticize ESP32 to be a little bit less deterministic compared to other controllers. One of the reasons is that it actually uses the real operating system internally. It runs on RTOS versus some other controllers that don't run any operating system at all. So the Arduinos, the typical Arduinos and the Atmel controllers, they're pretty deterministic. They're probably kind of roughly the gold standard in terms of that. Everything else is either as good as the Atmel is or slightly worse, as seems to be the case with the ESP controllers. On another hand, we're talking deterministic in terms of microseconds, literally, and sometimes nanoseconds. And for most cases, a few nanoseconds difference is probably perfectly fine. I mean, we're not talking about ages here. We're talking about minuscule amounts of time. For some projects, yeah, if you really need something to take a few microseconds or less, or a few nanoseconds or less, well, then you have to very, very carefully pick the specific controller. But other than that, yeah, they're all fine. But again, the ESPs, as I mentioned, they're a little bit less deterministic. So that's one of their disadvantages.
So I will comment actually with that. I was a little slow to get into some of these microcontrollers, Arduinos and such. And then actually I saw Boian's presentation he did on when he first introduced Visuino. Funny story. This is totally true. He announced this and he's like, yeah, it's $199 for no, $19.99. $9.99. Yeah, he said it's only $9.99 to get started. I'm like, oh yeah, $1,000. That seems reasonable. It seems like a really powerful system. And then as we're doing Q&A, he said something again and said $9.99. I'm like, wait, it's less than $10? He said yes. I said, oh my goodness. And I actually went out. It was during a code rage, and I went during the next session and bought a copy of it. I'm like, this is just too amazing. And then I started playing with Arduinos and ESPs and stuff like that. And it's not that expensive to get into the hardware. And when you actually start messing with the hardware and hooking things up and trying to figure things out, you'll learn a lot. And so a lot of your questions, you'll probably figure out pretty quick with a little experimentation. I'm a big fan of experimenting. So there's a question here. Can you have various execution rates for the Visuino blocks or groups of blocks?
Execution rates? Yes. Well, the answer is, generally speaking, yes. There is a concept that's called clocking, and we kind of use some clocking, though we used it on the Delphi side, but the same clocking functionality is available in Visuino. So if you want certain component to execute with certain reduce rate, you can add a clock component, set the rate of how often that component should be executed, connect the clocking component to the clock pin of the component you want to clock. And that's it. Yeah, it's you can have variety of clocking rates for a variety of components, and that's quite often used.
Yeah. Can you, let's see, I've lost it. Can you use multiple shields that you stacked? Actually, I think you showed that at the end. So
yeah, we already showed two shields stacked together. Again, with shields, you have to be careful. You have to read carefully the documentation, because each shield uses a certain number of pins. And sometimes two shields can use the same pin and they can play together fine. As example, two shields can be I2C shields, and they of course can coexist on the I2C bus. They can use SPI bus and share it as long as they have separated chip select signals, right? So the chip select as a minimum has to be different. But if one shield uses, as example, SPI, as was the case today, and another shield uses, as example, pin number 10, as was, if I recall correctly, with the potentiometer shield, well, you cannot. Then your as was the case with me when I started playing with the robot. I wasted half a day wondering why the hell my Wi-Fi shield is resetting and debugging my own code, believing that I have screwed up, until I suddenly slap myself on the forehead and look at what pins are being used and discover, oh boy, we have pin conflicts between the two shields. So the two shields are simply not compatible with each other. So as long as the shields use different pins and don't use conflicting pins, yeah, you can stack them as many as you want. But yeah, you have to be careful about that.
Yeah. The question here, was Visuino written in Delphi?
Absolutely.
Why do it the hard way, right?
Yeah, I mean, yeah, that's a straightforward answer. What would be a better tool to use to develop Visuino than Delphi? I mean, Visuino is literally Delphi at heart.
I've seen a lot of Delphi, or a lot of developers use Delphi to make other development type tools. It's something about Delphi, just, as a developer, it just tickles that part of your brain. You're like, oh, I have to make more development tools with it. So yeah.
It's more than that. If I may interject, it's more than that. Delphi is effectively, practically the only tool that can be used to develop something like Visuino. Well, that's not entirely true. You can theoretically use C# as example, but there are few elements that are absolutely necessary in order to achieve what Visuino achieves. And it requires to have RTTI effectively, because you have to be able to reflect the components, load them, store them, and so on and so forth, and of course edit them in property editors. There are practically only two languages that satisfy that requirement at present, and they're C#, I mean, and .NET languages, and Delphi. And the other requirement, if you really want to deal with native code, then you're down to Delphi only. And with Delphi, of course, you have at least the theoretical option to port it to cross platforms, which is something I'm working whenever I have chances to port Visuino. So that limits the option. It practically limits the options to Delphi only. If Delphi was not there, Visuino probably would not have been even theoretically possible.
Wow. That's a good point. One of the things I love about Delphi is it gives you that power and flexibility, productivity you'd expect from like a managed language like Java or C#, but it gives you but you're natively developing. You have a lot of more flexibility, I think, than you would otherwise.
Absolutely.
Does your Wi-Fi library for packet buffering and motion rate estimations apply to the gaps to smooth the motion?
Would you repeat the question?
It says, do the library tools provide for Wi-Fi packet buffering to some depth and motion rate estimations applied to the gaps to smooth the motion? I didn't see acceleration and deceleration properties.
Yeah, there is acceleration and deceleration. We actually entered that on the robot side. And the robot actually, albeit jerky, and we could have smoothed it more, albeit jerky, it actually had a certain level of smoothing, and we did that with the ramping components. So the general philosophy of all of my libraries and Visuino is I try as much as it is possible not to make complex components that do everything, but have individual components that do individual functionalities that allow you to put them together like Lego blocks. So for this purpose, we have communication components that do nothing other than communication. And then we have smoothing components that do nothing other than smoothing. And then you can combine them in the way you want them, and you can configure the smoothing components the way you want them. In this case, I just use the default values for the smoothing components on the Visuino side. If I had played a little bit more, which I was a little bit tight on time recording for the session, I probably would have achieved more smooth operation. And if we have used UDP instead of TCP, and I made arbitrary choice to use TCP just for the experimenting. With UDP, we probably would have had a lower latency, and because we wouldn't have had buffering, we would have had smoother operation. I was just curious to see how the robot will work if the robot connects to a centralized per se server, right? I mean, it was for me also experiment. Usually I make the robot to be a server and I send UDP or TCP packets or TCP stream to it. In this case, I decided to do the reverse, just first of all to show everybody that it's possible and how to do it. And second of all, because I mean, I wanted to experiment and see for myself what challenges there are. And obviously, jerkiness was one of the challenges we have experienced here.
I love that experimenting and figuring things out. I enjoy that so much. I guess I think that one was answered. Could you use the intelligence lab for teaching a hexapod to learn about layout or terrain?
The answer I would expect is yes. That's something I may have to try one of these days, but yeah, theoretically, there is nothing stopping you from doing that. I actually, good point. I actually got a new robot here that I just recently finished assembling. It has accelerometer and gyro on board. Typically, the robots don't have that. This is a new version of the smart car. And yeah, let me quickly bring it for everybody to enjoy. 1 second.
But I will add a comment here. If you're not following Boyan's YouTube channel, I definitely recommend that. And there's another YouTube channel. If you follow him on social media, he retweets Arduino projects as well. There's just so many great little projects he's working on you can find out about there.
Here it is. I have placed a separated Arduino. I wanted to preserve the firmware on the bottom Arduino, but this is the robot. Now ignore the fact, ignore the fact that it has two Arduino boards. I simply was mapping the shield for Visuino for the current release and just plug the shield to another Arduino. But nonetheless, the robot has MMU on board. So it has accelerometer and gyro, and it also has Wi-Fi and camera. So it will be fun to control. But the fact that it has accelerometer and gyro, you can track effectively the movements around of the robot, which will allow with things like Intelligence Lab and of course with the Wi-Fi on board to actually start training it and do exactly what somebody was asking, except this is of course not hexapod, it's a smart car, but the same thing. I mean, in terms of moving around the room. And one of the challenges is you need to know where the robot is located. That's why I was pointing the fact that this particular robot has IMU, because it knows its orientation and acceleration in space, which allows you to, up to a certain extent, reconstruct the movements of the robot.
Okay, great. Can you put in a link to your? I don't think the slide didn't have your link to your blog and your YouTube channel.
I will edit then the slides and send you a modified version of the slides. Yeah, okay. I was putting resources that were related to the particular presentation, but I can extend the resources, sure.
I follow you on Reddit and Twitter and YouTube and your blog. I try to follow you. There's so much to follow, but I discover new devices and learn about new things and stuff all the time from you there. There's a question here. It says you're using the Wi-Fi and Bluetooth. Could you do it with RF signals like 633 megahertz as well?
Well, if I understand correctly the question, this type of modules if he's referring to the corresponding modules, this type of modules are typically serial communication based. So yes, the project will work exactly the same, and you can reuse exactly the serial communication version that we did initially. Remember, we did it through the USB port. So if you plug the device with something like USB to TCP converter, I'm looking, well, I have one on breadboard here from project, but if you use something like this and connect the module, that I mean the serial communication on the module, then here with the USB you can send the serial communication and then you can receive it on the robot and do exactly the same thing what we did with the Bluetooth.
Okay. There's a question here about, are the libraries you're showing, are they free or are they commercial?
They are free for personal use. I make all the libraries available for free for personal use. Some of the visual components will have a small message from them that says free version. Other than that, everything will work perfectly fine and will work the same as I demonstrated. And Visuino has also a free version that has certain number of limitations, but if I'm not mistaken, every single of the projects that I demonstrated can be done with a completely free version.
Yeah, and they'll work with Delphi Community Edition as well. So, and I will say, yeah, you'd have very generous free personal use, but then your libraries are reasonably priced as well. So, I would definitely encourage people, if you can, to support Boian, so you can keep making all these great stuff. I'm a big fan.
Thank you.
Can you use this to control CNC machines?
Yes.
Does the code use hardware or use software or hardware interrupts for timing?
The Visuino code uses hardware interrupts for timing. Well, I mean, on the Windows side, there are other forms of synchronization. The libraries typically use the media timers, which are considered to be the most precise form of synchronization under Windows. So I'm simply hooking to the media timer API and using that thread for synchronization.
Patrick says, for the next conference, you'll put a rover on Mars.
We'll have to work on that.
If you could put some of your links in the chat window there on the control panel, some people are asking for.
Sure, yeah,
sure.
And you also should have, yeah, I'll have to reopen the links because I don't have them open right in front of me. Yeah, I probably can do it after we finish if there are some other questions because I have to search for them here and find them.
Okay, we do have to, actually, I do need to go so we can get the next session going. So
if you can leave this session open or something for a few minutes, I think you guys are using separated sessions, then I will be able to post them.
I will do that.
Okay.
All right, great. Thank you so much, Boian, and thanks everybody for joining us today.
Thank you. So yes, if anybody can still hear me, I will put the links now. I'm not sure I can see the exact questions. They're at least not refreshing on my screen. But I will put everything in the chat. And thank you, everybody, for joining and watching the session. Okay, I have figured out how to see the questions. There was a window that was actually collapsed. So last chance for anybody to ask any last minute questions, and then we can wrap up the session. And you guys are very welcome. And again, thank you everybody for joining. Okay, well, thank you everyone. Goodbye.